Easy, I think. So to be honest, in this paper we have a lot of concepts completely new for me. A lot of quantum concepts and physics concepts. It was crazy, really difficult.
They said Juan Pablo chose this paper.
They said Juan Pablo.
Yeah.
What
Yes,
paper was this
it's
again?
crazy.
They said Juan Pablo, and from what I've heard, Juan Pablo's questions are easy.
I hope so because the paper this is hard. Like at least.
I don't want to do the
Juan
paper, but because Juan Pablo said it, maybe I want to do it.
Oh, I like this paper better than the other paper.
Really?
The idea, I mean, this is nice.
I thought it was easier to understand.
Really?
Yeah.
I thought it was hard
I
to
mean-
understand.
Some of the concepts I didn't really dive into deeper to understanding, but I didn't feel like I needed to understand the paper.
Yeah, like an overview.
It's also a
yeah.
smaller paper. So.
Yeah, like an
It's
overview.
shorter than the other one.
Yeah.
Every small paper, yeah, this
It's-
one's smaller
Yeah,
or
this is
shorter
small.
in
How
length.
many papers? How many pages are there?
How many papers? No, man.
This is 4 relevant pages, and the other one I think was like 5 or something,
Yeah.
5 or 6.
That was 6.
Okay.
Yeah.
Here. Oh, it's here. Sorry. I'm with two devices. So the idea is, the main idea of this paper is like they have this kind of 2D perovskites. They change the number of layers in the crystal perovskite, and also like the structure here is this one L2 A M X in the same idea, but in this case L, it's like the large organic monovalent cation that we have over there in the structure. And we change the number of layers of the perovskite crystal. So we have 1 and 2, and then the idea is to go from 2-dimensional to 3-dimensional perovskite
Wait, you said
crystals.
what's the L?
L is the large organic monovalent cation.
Yeah,
It's
organic.
cation. Yeah,
so
it's-
so they put it on both sides?
Yeah.
Oh,
So
okay.
this is L, and use
It's
the
like a
perovskite in the
benzene
middle.
ring or
So
something.
why they do that? So
Mhm. Why?
the idea is they wanna change the energy, or is the energy split of the exciton that they create. So they can have excitons like in a larger time. They can
They
change the
increase.
existence of the exciton. So you
Yeah.
have a hole and an electron, you can keep that hole and
Exciton.
electron for more time.
Okay.
That's the main idea. How? Because if you add these organic cations, you create a wall, a quantum wall. Well, a quantum well. So, and that's the main goal of this paper. So, here it's a better thing to understand. These natural quantum wells. So, if you notice, in all of these cases, we have some kind of type 1 quantum well, where the cations work as a barrier. We have different types of quantum well, I didn't know that, so I just looked for that. And in this case, we have the type 1, which is the cations works as a barriers. So that means you change your conduction and valence band to create a quantum well in the middle. I don't know if you notice the figures. So in all the cases, right, the organic cation is a barrier. So and in this space you will have the
The organic cation is a barrier.
yeah, it's a barrier.
Barrier to
Because you can have the opposite. So you can have there is a type 2, for example, where you can have the opposite. You can have not a barrier, like a lower conduction and valence band. Like
okay.
I'm talking about this one. So if you notice here the cations, so here the conduction valence and conduction band are, the conduction band is higher than the perovskite, right? And the valence band is lower than the perovskite.
Yeah.
So you create in this way the quantum well. But there is a type 2 where this is the opposite. So here you have a lower one and this is higher. And it is also like a quantum well.
Like the way you showed these ones, I actually thought like maybe the second one is a type 2 and the third one is a type 3.
That's
No, all of these.
Yeah, but they are
no,
all
no,
this.
no.
Yeah,
All of
I
these.
just see that the well is becoming smaller.
Yeah, but all of these are type 1, but we have type 2, where the conduction and valence bar are different from the crystal.
So the
That's
wall is
idea.
when the energies are furthest apart, no?
Yeah,
Okay.
but you create different walls, right? Like, it's not just, I mean, it's not the shape, it's the difference between energies. And
Yes.
if you have
That's
difference
the-
between
yeah.
energies, you can have,
That's why.
yeah, okay.
It also affects the shape.
And if you notice there, when you go from one layer, right,
Mm-hmm.
2 and then more layers, yeah, for sure the difference in energy when you have your electron and the hole, the exciton, is lower, right?
Decreases.
So,
So the perovskite dominates.
So the idea is, yeah, the perovskite dominates that. So the idea is, yeah, for sure you have a lower band gap, but the exciton does not exist for more time, like for a longer time in this case.
So you
That's
have
the
a
idea.
smaller band gap, but the exciton. When you go to the type 3, like position, the third one, the red one. Okay.
Yeah, yeah.
Okay. So the exciton exists for the same amount of time or less?
Less.
Where's
What do you
time
mean?
on
In the
this graph?
three-dimensional case, yeah, less
Hmm?
amount of time.
Where's time on the figure?
Uh,
What's time?
no, it's not time, but it's on the paper. Like it's not
It's-
necessarily.
Is it physical disease that we're talking about?
It's not time, according to my understanding. I mean, they say it exists for a more longer time, so you can modulate. You can have the electrons and holes
Okay.
in order to study the electrons and holes separately.
That
Because
is-
if you have used the semiconductor and you have, you put some light, and then you create electron and hole that recombine so easily and so
Right.
fast, you cannot study the electrons and holes
That makes
separately.
sense. But like for those three structures, which one exists? Which one has an exciton that exists for longer?
The first one,
The first one.
Yeah.
With the greatest
Exactly.
energy difference.
the
Okay.
first one.
So you
Yeah.
want a greater energy difference.
Exactly. In this case, yes. In this
Okay.
case, it's the opposite. So
Oh,
we're
that
not
makes
looking for
sense.
the lowest to get, I don't know, more quantum efficiency or no. In this
Nah,
case,
you
it's
don't
the
need.
opposite.
Yeah.
Yeah.
Because if they're
no.
closer
You don't
together,
need
they could just recombine easier because it's like the lesser energy.
Yeah.
Oh, okay. Less energy.
That's the
variance.
idea.
Okay.
And these kind of 2D perovskites, that consist like in two-dimensional perovskite with something else, are called RP phases, which is Rudolf for whatever phases. Let me see if I have here.
Some guy.
Yeah, Rudensling Popper phase.
Good job,
If you-
Popper.
this is crazy, but yeah.
I see. They might just ask that question. What is the?
No, please, no.
Did they explain it in the paper? What that
No,
is?
they just mentioned.
Yeah, so they will ask you. I've
Maybe.
seen a similar question like that
Really?
in the past questions.
Oh.
That's
Yeah.
what I feel.
Okay, I think I have a note for that.
Wait,
So-
Rudolph who?
The unique crystal structure environment of 2D perovskite causes this state to split, so they no longer share the same energy level. This splitting is what we mean by lifting the degeneracy and the Rudensling proper phase. So the idea of the 2D perovskite has a different environment. In this case, the larger organic cation, right, makes the energy to split. And that split of energy is the rule whatever name.
That's that.
Phrase, yeah.
It's what-
Yeah.
like we're doing. Yeah.
And,
There's some more physical space, right?
Energy skills.
Well, the cat has a much
More
bigger.
energy. Sure. Yeah.
This makes the energy
Oh.
levels.
and
I like
here
the physical.
actually you can see that thing. Oops.
No, this-
Here you can see that thing. So this is crazy. Yeah. This
Yeah,
is
lots
crazy.
of concepts. I think.
Yeah, a lot of things. So that's why I write all of these here.
Yeah,
So
it's good. It's good.
we have G, which is the ground state, right, in our material.
Got that one.
X and Y. X and Y.
Sorry.
What?
No, sorry.
X and Y are the two other states that you create in this kind of environment with the 2D material, right? So, what?
Is it the electrons and holes?
Yeah, the electron, but yes, but we have two states.
Wait, that's like the
This
Rubinstein
is not,
degeneracy thing
yeah,
that you
but
split
it's
up?
not degeneracy because it's not the same energy. It's a different.
Degeneracy
It's,
means you're at the same energy.
exactly. So in this case, you have different levels of energy.
So there's the energy level splitting. Okay.
Yeah, exactly. So we have different energies. So
Right,
you don't
yes,
have
yes.
you don't have degeneracy, right? That's the main difference here.
Looks like the tree.
So X and Y are the linearly polarized orthogonal excitonic state relevant to the study. Due to the splitting and polarization of the Bragg excitons. Okay, a Bragg exciton is an exciton that creates light. I don't know if you don't know
That was
this
helpful,
big,
thank you.
yeah, this concept.
It's an exciton
C
that
is another
creates
state.
light.
What?
You said it's an exciton that creates light. Oh.
Yeah, it's an exciton. Yeah, that when recombines,
Oh, when
create-
it recombines.
creates light, right?
Okay. Okay.
When it recombines, create light. That's the difference. Because you can create an exciton and then I don't know, recombines and create heat or something else, right?
Ah, okay.
Yeah, that's
Nailed it.
Nice.
that's the main point. C is another state, but in this case is out of the plane. We are gonna talk about that later. So the idea is we have in plane and out of plane in this case, depending on the 2D perovskites. And D, it's a dark state. I don't know why they mentioned this D, because it's not relevant for this study, but they mentioned their dark state. So it's also existing there?
Yeah, I saw it as like, so an electron and a hole have spins of 1 plus or minus 1/2. And so when the electron and the hole spins are opposite, their total spin is 0, and so it's dark. But when their spins equal 1, then you get 3 sublevels, and that's where you get like bright states, dark states, where like they couple with light due to a favorable symmetry at a bright state, and that's why they emit light, because you have like, what is the MS, like the spin of 1 or of 0, and then the dark state is it's forbidden from absorbing light, because it has like the spin of like, you know, it's basically like the combination of spin of the plus and minus 1/2 spins of the electrons and holes is what creates like the dark, the light. And then I looked at it was like singlet, triplet stuff.
Okay.
Yeah.
Okay.
That part
Yeah,
is
now I'm
crazy.
thinking about Jablonski diagrams, and they could just ask you about those things.
Yeah, so the bright state splits.
Is bright state XYZ?
Bright state is Z.
Yeah.
C.
Just Z.
Yeah.
Dark state
Well, it says this is another
Yeah.
bright
The
state.
exchange interaction
They see
between
that in the
spins.
X and Y are also bright states.
Okay.
Yeah,
X
so it
and Y are
says
also bright states. Yeah.
exchange interaction between
Yeah.
spins of electrons and holes splits the bright states and dark states. Depending on the symmetry of the system, the degeneracy of the bright states can either be partially or completely lifted. And the completely lifted, that splits into 3 different sub-bright states, which then talks about like polarization and stuff like that. So
Got
it's
it.
just like electron and hole spins.
Okay.
Yeah.
Okay. What's next? Okay, here they make this study of photoluminescence, right? And reflectance for the samples with different layers of the perovskite crystals, right? If you notice, the energy increase when the number of layers decrease, right? And also, if you notice, when we have used one layer in n equals 1, we have an x and y peaks. So we have a really clear x and y, which correspond. They are trying to characterize these states, these new like energy levels that you create with the 2D perovskites. And that's why they make this plot. It was not difficult to understand, like when you have N1, you have X and Y, then in N2, this X and Y states starts to disappear, right? Because you don't have more this difference of this splitting of energy, and then with N4, right, 4 layers, you just have like the normal conduction and valence band. You don't have any split of
There's
energy.
No more excitons. You can't see them. They go
Yeah,
south.
like there are excitons, but you are not increasing the band gap to keep the excitons there. That's the difference.
Gotcha.
They said N is inorganic layers.
Yeah, the perovskite, yes.
The perovskite.
The perovskite,
So
yeah,
this
for
is the
sure.
perovskite layers.
Yeah, the
Okay.
N are the perovskite layers. That's
Okay.
that's the main idea.
So you're saying like as we increase the number of the perovskite layers, then the energy decreases?
What? Say it again?
As we increase the number of perovskite layers, then the energy decreases?
The energy decreases. Yeah,
Energy
we
between
saw
valence
we saw this here, right? See, if we have
So you're talking about the
more
band gap,
perovskite,
yeah.
exactly. If we have more perovskite, see the band gap is lower, right?
Yeah.
That's the main point. And here, it's a relation with that. And actually, so if we notice visible in the reflectance spectra, shift toward lower energies, right? If you go to lower energies, is an indication of decreasing quantum and dielectric confinement. Let me see. Lower energies. No, this is the opposite actually. Shift toward lower energies is an indication of decreasing. Oh no, it's okay. It's correct. So visible in the reflectance spectra, shift toward lower energies, an indication of decreasing quantum and the electric decreasing of quantum and the electron confinement. Why? Because now we have lower energy, the band gap is lower, so we can just create the exciton, but we cannot separate. Yeah. So
Wait,
Going more
what are you talking about? It's a
Oh,
decrease
it
in
should be
what?
less confined because there's less energy.
decreasing quantum and the electron, decreasing quantum and the electron confinement. Yeah, because if we are going to N1, so higher energies, we increase the quantum confinement. Because now the exciton, like, you know, if you separate, right, you
Mhm.
have this, now the quantum well, you have the exciton there.
Yeah.
But if you decrease, what happened? Now the exciton can be combined really easy.
Yeah.
That's the main point.
Wait, so you're saying as we increase the layers, then there's more quantum confinement?
Oh.
No, if we decrease the layer, no increase.
If you
Wait, if you
decrease,
decrease the layer?
Yeah,
No, I thought it was
decrease-
an increase the layers, then
No.
it decreases the band
No.
gap and decreases the.
no, you said
No.
when you.
When we decrease the layers,
Mhm.
we increase the quantum confinement. We increase.
We
the quantum.
increase. That makes sense.
Yeah.
Yes.
If we decrease the,
We decrease the
if we
quantum.
increase the layers, right? Increase the layers, we decrease the quantum confinement.
It's all a band gap
Right.
thing. Yes.
Yeah.
There's like
It's
it
just
goes
one-
on. It's like weird because can you go back to that one graph?
Yeah.
The two that one. It's like what is that Z plot even? What is that Z
Distance.
distance?
The organic layers.
Oh, I see. Okay, so then they're just saying that there's more area where and more probability where there's like less confinement basically because of the lower band gap because of that thicker organic layer.
So increasing and decreases confinement. What is this recombination thing?
It's
I've
when
never heard
the
of this.
electron goes back again.
Electron
To the hole.
negative, hole positive, want to go together.
Oh,
Okay.
okay. That
Yeah.
makes
So
sense.
you have the valence band, right? And then you just take an electron and go to the conduction band. But if that electron comes back,
Oh, so when you increase n, you have the space is smaller, and so they want to like the holes
Exactly.
want to be filled by the electrons.
Yeah.
I see.
yeah,
Yeah, so you're saying that the lower layer is more confined.
it's more
than the green one.
confined. Yeah, for the other one. That's the main point. And then
That's because there's less area of the
Here.
area that's at that certain band
That's
gap.
okay. Which is the next one.
And in
This
such a more 2D approximations as to use the structure.
And here they wanna kind of understand, right? Something else. Which is because it's crazy. This is crazy.
Something
So it
else.
depends if the light you're applying or you're getting is polarized or no. So
Right.
and it's related with electric field. If the electric field is in plane, this is polarized or
Right,
linear.
right.
If it is non in plane, that's circular or
Circular
the-
polarized.
yeah, circular polarized. So that's why it's a lot of physics concept. So I have some notes here. So in this case, they have for the figure A, right? This is a reflectance spectra with linear polarizations, pi x and pi y. So, but in this case, it's used for n equals 2, and they wanna know, right? In this case, this energy shifts between the transition between pi x and pi y, which correspond to the polarizations. Why? Because this is a signature of the bright exciton FSS, which we are going to talk in a moment. What is fine structure splitting means? The fine structure splitting means that in easy way, how I understand, is you have the energy and you split the energy due to the environment of the 2D perovskite. And that's why they are using this bright exciton FCC to understand how that split like occurs or which state correspond to exactly to what it is in this environment, right? And they made this kind of plots. The A is the one with use the n equals 2. If you see the plot B, this is dependence of the reflectance spectrum for again n equals 2 versus polarization angle. So they change the angle, right? And if you notice, there is a pattern between 0 and 180, because this is the cycle, you know. 0 and 180 it changed one time. Then again from 180 and 360 it changed another time, right? And that pattern it's related with actually the energy of the new states, right? Oh, I have some notes because this is crazy. I didn't understand very well. Let me. Yeah, I need to remember. I need to show you
Is
this.
this the energy of the exciton itself or the energy of the like bright state? Or are those the same thing?
It's the same thing because it's the same thing.
Okay.
Are these models or are they actually measured?
So
Yeah, they're models.
so V it's a way how they measure how the reflectance is changing with a polarized light, right? Because you are like using the light with different angles, so now you have
It's gonna be constructed with
But- yeah.
Okay.
So
That's a word.
and that's related with the electric field. If we have light and electric field, it's in the same direction, right? This is linear polarized, and when we change the angle, we change again the electric field in the light, and if we change the electric field in the light, so now we have circular polarized, and that's related with the energy of the states that we are trying to look. And then in C, they use the energy shift dependence, right? And how the energy change, and they mentioned they use this plot, right, to calculate which is the difference of energy, which I have over there, between the states that we create. So if you remember these states, right here, they want to calculate exactly the different states. So they want to calculate which is X, which is Y, which is Z, which is the value, right? Which is this difference. And they use this energy shift. They didn't mention how, maybe that's a question, how they use this C, right? How they use this data to calculate this energy shift. I don't have any idea how they
The last figure.
Yeah.
Okay.
how they use this last figure to calculate actually the energy shift. But that's the main point of that figure.
How about like the figure B? What's it about?
The figure B is related with a polarized light.
Okay.
Because you change the angle, right? So now you have linear or circular light, polarized light, and that's why they study this
Okay, so what does the red mean? What does the blue mean?
intensity.
Yeah.
Intensity.
Magnitude.
Yeah.
Okay, so like I'm just trying to see some patterns. So like if you say okay, you are 90 degrees, right? That you correlated with the energy you produce at 90 degrees or something.
According to my understanding, the only main point here is the cycle.
It's a
So
cycle.
yeah,
Okay.
so we notice that every cycle repeats every 180 degrees. So if
Okay.
we are from 0 to 180 degrees, this is one cycle, and then another cycle, and then another cycle, right? And that cycle corresponds to the excitonic state that you are
So
creating.
this is the energy of the light that comes off, not the
Right.
actual X.
Here
Looking at what energy
is the energy splitting as a function of the number of high inorganic or triagonal layers, right? Extracting for polarization. And they made this plot taking into account the previous one that I told you. How? I don't know. In this case, if you notice the energy splitting just decrease when you increase the number of layers. The same thing that we talked from the very beginning. So it's just like a summary of what we said, but they had the values, right?
I think
In
it's
this case.
the amplitude of that way.
In the previous one, yeah.
The delta E is the amplitude. And C. I think that's
Oh,
what
I
it is.
Do you think it's just kind of?
The amplitude of the wave in figure C there
Yeah.
is the value they're plotting in the next figure.
You mean
Okay,
figure
let's
B?
go.
So it's kind of
Figure
like
3.
oh,
the
figure
next-
3. Oh.
What we were just looking at.
Oh.
If we can change the slide.
Yeah, Oscar.
Next
Which
slide.
one?
That. I think. So the amplitude of that cosine squared wave or whatever it was is delta E, the change in energy. I think.
That makes sense.
No, yeah. Actually, yeah, it is because they show an equation with the previous one, with this one, right? When they make this degree versus energy shift,
But we're
you
just
can create the equation which shows that graph,
Yeah.
though, like this pattern. And with that pattern, they get something like delta E equals to cosine something.
Yeah.
Yeah, it's the equation. Yeah, in the page. Which page is this?
Then where does that come from? So
Yeah. Yeah, from the figure 2C, they get that equation, and that's the delta E.
Oh, the delta equals like
Exactly.
delta
Equal-
cosine square.
Square, yeah, this one,
Oh,
this
okay.
one, this one, this one, exactly. And then with this one, they made it explode.
But what are they putting in?
I think it might be where those white lines are from the previous one. It might be just a sense of that. I'm so not sure. They say the white lines indicate the energies of the two states.
Oh, okay.
And
Alpha is the
then
detection
the difference
angle.
between the two features, and
Phi
then
is the
it's
phase.
something in between.
But is the figure or is 2C just for n equals 2?
Yes.
Oh, and then they just apply that to n equals 3, 4,
Yeah.
and then that's what the figure 3 is. I
Yeah,
see. Okay,
yeah.
that makes more sense.
Yeah,
Yeah, yeah, yeah.
yeah. And
So
then-
what is it? So energy splitting decreases as n increases.
Yeah.
Why?
They are, why?
Yeah.
Because the quantum confinement decrease.
Oh, so with less quantum confinement, you get less splitting?
Yeah.
Why?
They are trying to explain
Okay.
that. Yeah, they are trying to explain that with the values, right? I mean, it's they. I mean, why? I think is not the question they are trying to answer. They are trying to answer how instead of what.
Okay.
Because why is use the quantum confinement.
Yeah, but like I guess maybe this is where it's like more physics and quantum based, where it's like, why is it that when you have less space, that there's less splitting?
There's different equations that govern 2D stuff. Like the electrons can act different, your atoms, you can have something different, so it's just different governing equations.
Okay.
And then there's gotta be some sort of in between. So yeah, the way I think about splitting is, okay, there's two things interacting. It's gotta like meet in the middle somehow, but it's still quantum, it's still discrete, so you just have a bunch more energy levels that can occupy instead. Yeah, if you look at pictures of like
Yeah.
splitting energy levels. but-
Yeah.
So with less space, there's less energy levels able to be, I guess,
Occupy.
occupied, and so because I assume like when you increase the confinement, there's way more availability
That's
of
not
energy
what it-
levels, so
I-
therefore there's a
But
more
you were
How,
probability.
how I think is like in chemistry terms, how you create a like a not a
Same
band
thing.
but
It's the same thing.
but a molecular orbital.
So
You
yeah.
have atomical orbitals, right?
Mhm.
Atomic
Same.
orbitals. You mix the atomic orbitals with a function, whatever, right? And then you have molecular orbitals. Let's think like you have millions of atomic orbitals because you have
Mhm.
millions of atoms, right? And then you create a molecular orbital, right? And more you just put over more and more and more and more and more, right? And that's create your band. Right?
Okay.
That's create your band.
It's
Now,
discrete levels.
Yeah.
yeah, and now if you have 2D materials, right? You have less atoms, less atomic orbitals, less molecular orbitals. So now
It can only
the
be in like two directions or something like that.
so
Okay,
now
okay.
you can see like because if you are trying to I don't know if I can
You would get exponents.
so you have
Yeah.
atomic orbitals right like lines and then you put more over then it becomes just one line
Yeah. Yeah.
right but if you decrease you can see the difference between the two states
Yeah.
Yeah.
that's why maybe it's the splitting
Okay, that makes sense.
but maybe we're wrong but
I don't know, that makes
It's
sense.
the same.
I mean, that's enough. That's what I wanted to know. I
Yeah.
like didn't understand anything more than like I didn't know why the like the space itself affected
and
splitting.
that's why when so for example when you're talking these kind of nanomaterials maybe correct me if I'm wrong but when you have 0D material that means the 3 dimensions
Mhm.
are confined into the nanometric like scale
Mm.
that means 0 to 100 right and in that case you for example fullerenes if you work with a fullerene
Yeah.
you don't work with just you can work with bands but yeah it's just it is a 0D actually right
Or zero.
0D because all dimensions are confined in nanometric scale. If you want
I
1D
see.
like nanotubes, just one dimension
Yeah.
is
yeah.
confined. What is no
I
2D?
see.
What 2 dimensions are confined, right?
Yeah.
In the and one dimension you can be whatever, right?
Yeah. Yeah.
And 2D is one dimension is confined,
Yeah.
and the other two can grow whatever you
I
want.
see. Okay.
Yeah.
And it's just a whole bunch of equations physicists made up because it's easier to call it 2D instead of, like 2.5D or something like that.
Yeah.
Everything's 3D, but
Yeah.
it's just their governing equations are different and approximations are really different.
Okay.
And the splitting is kind of weird in between in that. It's just some, quantum math having to work out.
Okay. It's enough for me.
And here, I have a lot to say about this. With A, right? This is crazy. So in A, they mention they go from 0T to 12 to 0T to 12T, right?
What's it, T?
And they use Tesla's. This is a
Tesla. Oh, yeah. Okay.
magnetic
No worries.
thing, yeah?
Yeah.
And they use something really specific, which is the B parallel K parallel C, which is has a name and I forgot it. This has a specific name.
Faraday's configuration.
Faraday's configuration, and Faraday's configuration means like your B, that is your magnetic field, it's parallel to your K, right? And it's parallel to the crystallographic axis of the material too.
What is K? Is that K the K vector?
Yes, the wave vector of the light.
Oh, they're all.
And that Faraday configuration means that. So the magnetic field is parallel to the vector and it's parallel to the crystallographic axis, right?
Just the math, yes. Probably.
And when they, if they go from 0 to 12T using n equals 2, you notice like the two signals, like 2 points, they start to shift, to separate each other, right? In the A1.
Is that the splitting?
Is the split.
Oh my gosh, that's
Exactly.
crazy. Okay.
So they are trying to explain why that happened, right? In this case, the N2, it's just, it's split with N equals 2, right? Applying different magnetic fields.
Where did you identify that those points there that are splitting are like what they should focus on?
That's an excellent question. I don't know, because they mention for one layer, for N2, I don't know, but they mention for one layer is well known that these two values, for example, in literature, these two values, X and Y, in the reflectance spectra, correspond to the splitting energy.
Okay, so
But that's for N1.
Okay.
And I
But they are
just
doing
think
this for N2.
for N2 because they have the 2 points again, right? And why they are doing for N2? Because just the data is better, I think. They do not mention why N2, or maybe I didn't pay enough attention.
Okay.
So they're
Yeah.
still splitting at N2.
Yeah.
But I assume is there still splitting at N3 and N4?
Yeah, but it's difficult to see. It's really difficult
Okay.
to see, right?
And that's, so when you increase the magnetic field, you get increased,
The splitting.
Splitting.
Yeah.
why does that matter?
They're showing that it
So
exists.
true.
Like,
That
that there is a difference.
But
There is a difference in the energy, the split energy.
but
But
it doesn't mean anything, I mean, it doesn't tell us anything we don't know.
to characterize, just to
Right.
characterize, it's there.
Shows you
The
that
splitting
their
energy is
math,
there.
The theory of how the thingy works, because they showed it with the magnetic field.
And then in the graph B, when you have N2, N3, and N4, if you notice, energies, right, decrease. The energy shift, right, between X and Y, decrease. Why? Because we don't have more splitting energy when we increase the dimension of the perovskite.
Oh, so the fact that the lines are coming closer together
Yeah.
means that the splitting is happening.
It's disappearing,
less.
actually.
Yeah, okay.
Yeah, it's
For
disappearing.
N3 and 4.
Yeah, because we increase, the layers of the perovskite.
Right.
The same thing that we told at the beginning.
So why is it that they all reach the same extreme values?
Quantum. It's just a state that exists.
It
And
says-
those are all this, and that's intrinsic to like the perovskite itself or something?
That
And
it's
it
a
doesn't.
3D thing. And that's the energy level of the
I'm gonna stop
3D
asking.
thing.
I'm not
Yeah.
doing this paper.
Okay.
it's crazy. It's a 3D
This is
thing.
never gonna make sense.
What
It's
else?
very
What
hard
else?
to
The
imagine
E
it's testing
You can't see it.
is
so
the
it doesn't-
diamagnetic coefficient. The plot on the E is the diamagnetic coefficient as a function of the number of inorganic octahedron layers.
What happened?
And the relation here is like, if you increase the number of layers, right, the diamagnetic coefficient increase. which is the same thing. We don't have
You
the
said they said
confinement.
as what increases.
Yeah, because according to what I read, is like the diamagnetic coefficient is also a useful tool to know there is confinement. So if you notice, the coefficient increase when the number of layers increase, right? That's mean there is no confinement. The same thing that we said from the very beginning. Because when we have one layer, we have confinement. But when you have more layers, the confinement just disappears. And finally, the final plot is the exciton. No, this is is the exciton factor in the direction parallel to the z-axis of the crystals as a function of the band gap energy. Which, do you want to say something?
No.
Which
I just confused myself in my head. Sorry, keep going.
which in this case is the same thing, right? So you know the excitons, when we have 2D, the exciton G2, which is one specific in the paper, I will show you in a moment. In the 2D, the energy of this exciton, you know the first is 2D, right? The first
one?
line. The first line is 2D, the other one
First
is 3D.
line from where?
And you have
Those say
like,
freely on it. Oh, the
2D, the blue one?
yeah, the
it's
blue
labeled
one.
there, right?
Yeah, it's labeled
Yeah.
here and this one, right?
It's G2.
And here we have N4, N3, N2, right? If you
That's
notice,
the gray line.
The one that he's,
Yeah.
The gray dash line.
That's
Yeah,
the y-axis
yeah,
on the one
yeah.
that he's pointing at.
so the one that we use here, I
exciton
forgot which is
energy.
the one that we use here. Let me see.
I think.
Excitons.
It's MA.
There was also something, yeah, that was gonna be my question at the end.
What?
It's like they mentioned G factor, and I don't know what G factor is.
Other people mention it too, like one people.
Let me see because I have this one.
And I think
Because
I
many
thought
many things that I
attempted to Google and I still didn't understand.
I yeah, it's related with the Siemens effect. Yes,
That's
yes.
another one of the
Yeah,
splitting mechanisms.
the splitting it's related to the Siemens effect. I have this here.
Yeah, exciton, G factor, and diamagnetic shift. The diamagnetic shift I understand, the G factor I don't.
I have this here. Let me see my notes in this crazy thing. Oh, this is some. Here I find something. I think it's important to mention here. Where?
That's the weak magnetic.
Here in the first one, in the A, you know, when we are in 12 Tesla,
Hmm?
Yeah.
like a strong magnetic field,
Yeah.
we notice that they are clear change in the spectrum, right? In the
Mhm.
reflectance spectrum. So we
Mhm.
have the energies, right?
Yeah, very distinct.
Why? Because let me see. Why here we have clear difference, and in the 0T we don't have clear difference? Like we have the difference, but it's not as clear as the 12 Tesla, right?
Mhm.
Wait,
Why
what-
increasing the
Difference
magnetic
in
field?
what?
Yeah.
The energies. So why is it splitting? Why now the energy? You know, the energy of one point is higher. Is the difference between the energy of the point, right? Is higher compared with
Oh.
0
Energy
Tesla,
difference.
right? The energy difference,
Okay.
and that's related with, I don't know. I just find this in a paper. Thermal vibrations.
Thermal what?
Thermal
Vibrations.
Vibrations.
Thermal vibrations. And I don't know why it's thermal. It's just
Energy.
it's just energy, but it's
Yeah.
the thermal one. Okay, it's just the thermal one. I don't know why thermal, because we are using magnetic things. I don't know.
Magnetic makes them.
Magnetics, it makes it split, so you can see the split. And that's why there's even a G factor in the first place.
Okay,
Because the G factor is. Wait.
and that's actually my FSS value.
I'm getting a better explanation.
What is the FFS? The difference, the fact that like
Define structure splitting. The FFS is the value of the energies of the different states that we create. So that's why they are using this thing, because makes the energy split. So you are showing that you have different energies. Because
so the
that's
fine
related
structure
with-
splitting is just the two different energies of
Yeah,
the two
that we
different
create
splits.
in the 2D,
Okay.
in the 2D, in
And
the
they
2D
split
perovskite,
more.
in the split more, yeah. So you can characterize easily if you have, you know.
They
the
split more
difference.
at n equals 1 than at n equals 4.
Yes, but in this
Oh,
case,
wait.
in this case, it's just n equals 2. In these cases, they split
Oh.
better when they have 12 Tesla.
But they all split the same absolute value now, right?
The same absolute value? No. What do you mean?
Like the total energy shift at 9 Tesla is pretty similar for 2, 3, 4. But you could say the splitting is more for 4 than it is for 2. Right?
But the energy difference is higher.
Energy difference is higher for 4.
I think the energy difference is pretty same. It's
Yeah.
almost the same. I
Difficult
think
to see.
I don't know.
Like
Like
You
I
see
think
the
this
lines?
is
The lines
I
is
think this
increasing.
is what you're showing, like the difference between this and this, right?
Yeah.
But that's with increasing in the same N2. I'm saying between N2, N3, and 4.
Oh,
they're
and
all
two
going-
and three.
these
Yeah.
guys?
Oh, this
they're all
one?
in the same.
No,
They are
because
different, right?
they are different. You know, like now the states X and Y are getting closer at 0.
Yeah, but I'm saying the final at 9.
Yeah, why are they at
nine,
the same?
and 9.
That's kind of confusing me. Is this a measure of like how much it splits as you increase magnetic field, or the fact that it just splits?
The fact you use a split.
Okay.
That's it.
Okay. Then it splits it all.
Yeah.
Because I think the G is like going to tell you how much it's the reference G, the G factor.
Oh.
It's like, is it the slope? It's maybe related to a slope in there somehow. Not quite sure.
So they all split at each end. It's just a matter of how much they split.
Relative
I
to where they
think so.
start.
The G one. Yeah. The G one.
Yeah.
Okay. And G
Or it's a
is
slope.
where they start, or G is the amount they
Slope?
split? The slope of the
Maybe?
splitting line?
I'm still reading.
That
I've had to
I don't know.
calculate
That's
G-factor
that's
before,
crazy.
and it's based on
I mean, we're not using 9 Tesla for a magnetic field, right? So this is.
I mean,
co-
yeah, that's a thing.
I mean, this is to characterize they split more, right? But if you know in 0 Tesla, which is like the real world, the difference between 2 and 4 is just big. That's the main point here,
So what do those two little black lines pertain to?
to show the splitting,
So that is the splitting, and that is not changing that much.
to show that there is a splitting energy of the state, and that's it.
But I don't
So
understand.
to show that when you have 2D perovskites,
Yeah,
you have new energy states.
I know, but
That's it.
why put that under like a magnetic field?
Because magnetic field works like show this is splitting better, according to my understanding.
Okay,
Right.
but like I guess because I do see it kind of like I do expect I see it going like this slightly. Is that kind of expected too?
Yeah,
Like splitting more with a higher magnetic field.
that's what I think.
Oh.
Quantifies the linear energy shift of the.
That's what I think. And in the other one, it's the same thing. So you're showing that when you increase layers, X and Y get close. So you don't have the split energy at the 0, right? At 0. When you increase magnetic field, X and Y get far again because magnetic fields separate your levels again, right? But at 0, get X and Y,
No split.
not a split.
No magnetic field. Like
Yeah,
there's
no
the
magnetic field.
equation 3.
Oh, that's magnetic field.
Yeah.
Which one?
B is magnetic
Oh,
field. So
yeah.
if you
Oh my
if you
God,
see B,
okay.
C,
I
and
just
D,
realized
right,
what
n
that
equals
graph is
2,
about.
n equals 3, n equals 4. At
Mhm.
0B, there is a split energy, right? In n equals 2, there is a big difference between X and Y states.
I
N
understand.
equals 3, there is a difference, but not as much, right? And 2 and 4, the energy at 0 Tesla. Why? Because and why that makes sense with the first one? Because this one, when you increase magnetic field, you increase also the energy difference. And the same with that.
Yeah.
For me, it's like this. So there is just n equals 2, but the difference energy is different. For me, it's different. And here,
And that's why
So
the
I-
G factor of 4 is higher than 2, is because in that graph it's going from a very small
To
split state to
To
a
where-
larger state. Okay.
Yeah.
Versus like at n
Oh.
equals 2, there's still a large difference and it doesn't split much more, therefore that's why n equals 2 is less in the exciton G factor.
Because it could be manipulated more,
Equation 3,
sort of.
I think.
Yeah.
Equation
The G-
3?
The G factor, that's right.
So just looking through equation 3, it's got a plus or minus in the front of it.
Oh,
Yeah.
yeah.
That's the two states, that's
Yeah.
the splitting.
Ah,
And you see there's a B term in there, so it only happens when there's magnetic field.
oh.
Yeah.
There's only a plus and a minus, there's only a splitting when there's magnetic field. and there's the G factor
Yes.
in there too.
I
Which is
see,
why
I
I'm
see.
saying it's maybe sort of related to the slope.
Yeah.
That's totally guess.
I think that makes sense.
Yeah, that's all I know.
Yeah, if there is no magnetic field, this is 0 and the other one is 0 and uses this sigma square, which is sigma, which is nothing.
Okay,
Right?
almost done? This one done yet?
Okay, let's
Oh,
see.
almost done.
Yeah, it's done.
Like, explain the last graph again. Like this one here, the G and then the band gap energy.
The G is related with this equation. I kind of understand
This
right
one.
now.
Yeah,
Better.
this one.
Yeah,
talked
so
about
see,
G
if there is no
factors.
B,
So they're saying
Oh,
that
yeah. Oh,
like,
yeah.
if there is no B, this is
up there
0.
between
This is 0.
the three.
The only term is this,
So you
right?
get a higher
Yeah.
G factor.
So there
with
is no
more
split of
layers,
energy.
is what they're saying.
What
There is a
is
split of
Yeah,
energy,
I
right?
think
There is
it's
one and a half
because,
split of energy.
like,
If there is B,
In
all
n
of these will
equals
change.
2,
We need
there's
to have
already
the
a
values,
very
right?
large
The values are on
difference
the plots.
at zero
All of this
magnetic
is
field,
it
and then
changes.
as you keep
So
going through and
There's
more
not much
and
more
more
So now,
difference.
yeah,
when
there's
you
not
get
much
the
more of a distance, which
difference,
is why I
right?
think n equals 2 is
It's
less than n equals 4,
when you
because
increase
it's like
when you
n
increase
equals 4, like
magnetic
it
field,
starts very, very
all of these values
close
will
together
increase
and then
this
splits
energy
off.
difference.
Do they have all the
So you
values
have
for
the
the G
split
factor
too.
in this or
I
no?
don't know what
What shows the split in this equation?
I have
The
no clue.
magnetic field
Okay.
B.
The magnitude
Because
of
this
the
is
splitting.
two states.
Okay.
You make the plot for the one positive, which is one line, and make the plot
Yeah.
for the other one negative, right, which is the other line.
Okay.
And
So
I
that's
have here
yeah, and
G
then-
factor
and
for
then-
electrons helps
and
determine
then
how
you
magnetic
calculate
moment
this
is
at the
affected by
final,
external
you know?
magnetic field.
And this is your final point.
That is a good
initial point. You can
sentence.
calculate
Yeah.
every
I
point.
don't know.
It's a very
Well, it's written down on my
Anything.
paper, so I must be
Isabella, what did you say?
or like ChatGPT did or something.
Isabella, what
I'm
did you
gonna
say?
take a picture
I
of your
said
paper.
the G factor for electrons helps determine how magnetic moment is affected by the external magnetic field.
Okay.
Where I found that I
I
didn't
kinda get that. Okay, so can I like stop recording or?
Oh, yeah.
You
Yeah.
can, yeah.